So we're going to go over this problem here, which is a bit of a stumper for many students. I think you see the plot and tend to sort of freeze up, especially if it doesn't look like something you've seen before, and it can be very confusing. And so we're going to try and answer it by digging back into some of the slides from the lecture notes and try and answer it, and I'll try and break it apart a little bit. Before we read, let's sort of look at this plot and try to understand, picture's worth 1,000 words here. So our axes say x and y in meters, so it's some sort of a positional graph, and it's about the voltage, and I have a scale, which is really telling you the volt at different positions, okay? Um, so all these lines are reminiscent of the equipotential lines, meaning equal voltage. And so let's go ahead and read and really see what's being asked of us. So consider the following map of the electric potential field caused by three charges. The color displayed shows the voltage at different regions, and the lines show the equipotential lines. Which letter region has the largest magnitude of the electric field? Which direction does the electric field point there? Explain why you picked that answer. So a lot of things feel not related. We're being asked not about the voltage or the electric potential. We're being asked about the electric field, okay? But there is a relationship between the two, which we'll talk about in a moment. A few things to point out here, or one thing here, is we're asked about three charges and not really told where the charges are or what are they. So we don't have a Coulomb value. But if you look at the picture, we see these three regions which something looks off about them, and those are indeed where the charges are. Okay, and so first, before we really get into it though, let's look back at the slides and try and understand what we're looking at. Now, recall this from around slide 18, 19 or so in the notes. Um, we had this picture and we were asked questions about the charge values like positive or negative given an electric field. So this is not the electric potential. This is an electric field with arrows, okay? And one of the takeaways was that we could tell whether there is something here and whether it's positive or negative, right? And so how we did that was all the arrows pointed towards the center, the arrows being the electric field, and we discussed that a positive charge in an electric field would flow towards the arrows. Okay, so if I put a test positive charge in this magenta region, since there's a rightward arrow, it would get pushed towards the right. And so a positive charge getting attracted towards the center means that whatever's at the center, it's not a positive charge, it's a negative charge in order to attract this positive charge towards it. Okay, so keep that kind of idea in mind. That might help you discern positives and negatives and directions of the electric field. Another slide that I think is important here is this one where we looked at the height map of a mountain. This is not to do with electric fields at all. It has to do with gravity, right? And we talked there are equipotentials here too. These lines that I've colored in are lines of equal height. This is the 1,500-foot line. If you're anywhere on that line, you're at 1,500 feet above sea level. And so one of the, like, if you're used to reading these kind of graphs, one of the things you're looking for in this topography is how close are these two lines, any two lines, right? And what does that tell you? So think about what that tells you for a second. If this is 1,500 feet and this is 1,000 feet, and it takes us this distance to get between them, then what that will tell you is how steep of a climb you would have to do to say hike up this slope, for example. And so if you were, really astute hiker and you got your maps out, you could figure out what's the grade of this mountain here at this region, or what's the slope. If, for example, it was 300 feet between this first line right here and there, then you could do rise over run. You're going up 500 feet across 300 feet, and that would be a slope of, I guess, 5/3. Um, and maybe that's too steep for you to hike, you know? So you would prefer a sort of more gentle path. So the equipotentials tells you where the heights are, and how close they are tells you about the slope. And so that brings us back to our problem. This is identical. It really is. I mean, electric field, charges, and gravity and mass, they're mathematically they're the same with a few minor exceptions in the math. Those two things are very similar. And so forgetting Physics 107 and just thinking of this as if I gave you a map of mountains and valleys, and then I asked you the question, right? Which of these has the sort of steepest descent, for example? And why can we look at it that way? Well, because we have that E delta S equals delta V was one of the equations. If we do a little bit of rearranging, E equals delta V over delta S. Now E here is not energy or anything like that. It's the electric field. And the electric field, this is saying the electric field is the change in the electric potential over some generic distance delta S. We don't use delta X or delta Y because we like the idea of saying, well, it could be X or Y or in some other random, any direction, right? And so we're saying that if the voltage changes over a little bit of distance, that is going to tell us our electric field. But this is a rise over a run. This is a slope. The slope of this graph, which is two-dimensional, it's not like a normal graph that you've seen in your math classes before. The slope is the electric field, okay? And so, so if we look at these and I ask you, well, think of this as a height map, which one has the steepest slope? I'll give you a moment to think about that. A, B, C, or D. And if you picked A, that would be the correct answer because each of these equipotentials is like a height line. It's like 500 feet, 1,000 feet, 150 feet, except instead of heights, it's really these voltage values here, 20 volts, 40 volts, 60 volts. And we see that we cross 4 or 5 lines in this A region, whereas B, we only cross 2 lines or so. Okay, and C and D, it's even less. So A is the correct answer to which has the largest magnitude of the electric field. Okay, and now which direction is that electric field? Well, we've got to decide about a little bit about the charges, right? In the same way, think about a mountain, and this is height again. Think about what way water would flow. It flows from the top of the mountain to the bottom, right? And so if we look at these values here, we grab the high voltage one, and this is like the top of the mountain. The low voltage one is like the bottom of the valley. This is like a positive charge, and this is like a negative charge. And so thinking about it that way, this is positive, and this is negative. And so what we'll find is that the electric field goes from positive to negative. If you recall, electric field goes from positive to negative. And so in that region, it is going towards the right. It's also always perpendicular to the equipotentials. You see, all these lines are perpendicular in this region to each other. The red line is perpendicular to the equipotential lines. So that's the answer to the second part. One more bonus question. Can we estimate, let me do a little bit of racing here. Can we estimate the electric field value in that region? And we can. So look at this, E equals delta V over delta S. If we were to find the distance, right, from here to here, which we can do since we have the values, that looks to be about 0.123, 0.3, I'll call it, 0.3 meters. is the distance. That's the delta S. And the voltage value, well, that might be a little bit challenging, but that's told that you can find by the equipotentials. Each of these lines is 20 volts apart, so 20, 40, 60, 80 or so. So that means that the delta V equals 80 volts, and divide those two values. 80 divided by 0.3, 80 equals 80 volts divided by 0.3 meters. That gives us 267 volts per meter. Very complex, very advanced problem, I think, at this point in time. But if it made sense to you, good. If it didn't, please, at this moment, write down any questions that you had, which part didn't make sense, and then we can start our class by asking about that, okay? All right, folks. Thank you.